Okay, so I want to start working on some legacy encoded SSE instructions, but also move on to some VEX prefix and EVEX prefix instruction encodings as well. So I thought that a good first instruction to do might be something like MOVAPS. So this contains all of the different encodings. There are these two SSE ones here, which are encoded in the same legacy way as all of the other instructions I've done up until now, but the difference being that they use these vector registers instead. So in this case, it's XMM, which is 128 bits wide. But it also has these AVX and AVX 512 instructions, which are VEX prefix and EVEX prefix instructions. So I'll start by just doing this MOVAPS one and then move on to this VMOVAPS, which is the VEX and EVEX version. So the main difference with this legacy encoded one is that this is using vector registers, so I'll need to start by creating some new variables to use as vector operands. So these will be basically vector 0 to vector 31. Although this legacy encoded instruction only supports up to vector 15, EVEX introduces an extra 16 registers, so you get up to 32 registers. So I'll just go and create that before I create tests for it. And actually also I'll need to add some new widths as well. So we've got QWord, which is 64 bits. We'll need XWord for 128 bits, YWord for 256 bits, and then ZWORD for 512 bits. And then down here I'll also create the operands for vectors. So we'll say the V0, for example, is operand. I'll need to distinguish between general purpose registers and vector registers because some forms mix both of them. So we'll have VEC as the flag for this one, and then we'll have the index as usual. And so these will just go, I'll do until, let's say, A, B, C, D, E, and F. Then we'll just do a copy of these. And then these ones will basically just have a 1 over here. And these are vector registers 0 through to 31. So I'll need that VEC flag as well, which I'll just add here. So VEC. Let's just make sure there's no errors. Okay, right. So now if I create some test data for the for MOVAPS, I think what I'll do is I'll just call this MOV SSE VEX EVEX.asm. So this is bit 64, and we've got MOVAPS as the first legacy encoded instruction. So this is basically, in these tables, they use these letters instead of the more explicit operand encoding forms. These basically correspond to these rows in the operand encoding table down here. So this is row A, B, C, and D, and then it tells you the usual, you know, in this case, A is actually just RM encoding, B is MR encoding, and then this one is RM and MR again. The difference being that when you get to stuff like EVEX, you also have these tuple types. And so they basically have these letters that are only useful in the context of the table that's directly after the encoding table. So in the actual encoder, we won't be using these letters at all. We'll just be using the existing operand encodings based on these tables. So in this case, although it says op_n is A, I'll actually be setting this as RM. Okay, so so MOVAPS here has RM encoding and an MR encoding. So if we do MOVAPS with, let's say, XMM 0 and XMM, I don't know, 3 or something like that. We'll also do some extended ones. So maybe we'll do, for example, 14 and 15. And then we'll have like a memory access. This is just a general purpose register memory access to generate a normal SID byte, as I have been already, so we'll just use RCX for this. And then we'll do one where we just switch this around. So I think this should cover all of the forms for MOVAPS. So let's just generate this. We'll do NASM MOV SSE. We'll create a listing file for MOV SSE.lst. And then we'll go to the encoder test and add a new test group. So I'll just add it down here. We'll say this is MOV SSE VEX EVEX. And we're going to have MOVAPS as the op here. This is going to be ZWORD because it's the XMM registers. And then the op one will just be, for example, in the first case, it would be V0 and V3. Then NA. Then we've got a test with some extended ones. So this is 14 and 15. Then we've got 2 with CX as a memory access. So that's all of the tests implemented. I need to add the mnemonic here. So this is MOVAPS. I'll also add VMOVAPS here because I know I need that in a minute anyway. And then we'll just go to the forms and add a new form table. Okay, so this, if I do a test here now, we can't match a form, and so I need to just add these forms to the table. So we've got a form with a secondary opcode map selection. Opcode is 28, and then when these operands switch around, the opcode becomes 29. So for MOVAPS, we'll basically just want to match on ZWORD. We'll do RM as the first operand encoding, but in this case it's actually going to be VEC and then VEC or memory. It's got the secondary opcode map, and the opcode was 28. Then we've got another one where the opcode is 29, but this is where the operands switch around, and the potential memory access can be the first operand, so this is MR encoding. Right now we don't have the VEX prefix coming out. That's because I think I need to change this is extended check. So this needs to include VEC in the check as well. Okay, so that passes. So now I can move on to VEX and EVEX prefixes. So starting with VEX, we'll just look at this notation because we're already on this page. Basically, this VEX here means that this instruction needs to use a VEX prefix of some kind. Then we've got 128 here, or 256. This is just referring to the bit width of the operands. So in this case, XMM is 128 bits, whereas YMM is 256 bits. Then this 0F says that it's the secondary opcode map that needs to be selected. The WIG here means that the W bit is ignored. And then that's followed by the opcode, followed by the mod RM that selects operands using the reg and RM fields, as I have done up until now anyway. And we can see here as well that the opcodes, so these legacy encoded ones are 28 and 29. Those opcodes remain the same for the rest of these forms as well. So they're all 2829. So if we just go up and look at the VEX prefix information here, so basically We can see that the same as legacy encoded instructions up until now, there's always still an opcode, a mod_rm, a sib, a displacement, and an immediate. None of this changes, this is all exactly the same. But the difference is that instead of having, for example, a rex prefix, or like an operand size override prefix, or, you know, opcode map selection prefix bytes, like actually being emitted as full bytes, all of this stuff is now compressed down into just 2 or 3 bytes in these VEX prefixes here. And the same goes, so, you know, with rex here, instead of having the full rex byte here, the extension bits are now just encoded as some bits into one of these VEX prefix bytes, and the same with like opcode map selection and things like that. So if we go down a bit more, this is the diagram of the layout of the bits. You basically have to choose one of these layouts. So you choose 2 byte or 3 byte. Basically, you just want to choose 2 bytes if you can, and only switch up to 3 byte if you need some feature that can't be encoded in 2 byte. So for example, if you need the X and B extension bits from the rex prefix, then you must use 3 bytes. Or if you need to select an opcode map, then you need to use the 3 byte one, or if you have to set the W bit, then you need to use the 3 byte one. Those are the only 3 conditions here that require you to use 3 bytes over 2 bytes. And so you can see here as well, the MMM field here is what is used to select the opcode map. But if the opcode map is 0F, which is the secondary opcode map, in this case, you don't have to encode it. This is just the default. So if you don't need any features of the 3 byte one, and the opcode map is 0F, then you can just use 2 bytes, for example. The other difference here is that the rex prefix bytes here, or bits here, are stored in 1's complement, so they're now inverted. So 0 means that it will now be extending whatever. So in this case, R being 0 will extend the mod_rm.reg, X will extend the index, and B will extend the RM or SIB base fields. So the important thing to remember here is just that these are now flipped around. So 0 means on and 1 means off. Then there's this VVVV field, which is in both of them here. This is how you select the 3rd operand, which MOVAPS doesn't have, so I'll just be I'll implement it, but we'll be ignoring it for now. And then things like these prefix bytes here, instead of outputting, for example, 66, you now just set these 2 bits. So 66 is actually 1, F3 is actually 2, and F2 is actually 3. And those get encoded in these 2 bytes here and here. So they're in the same position in both cases. And the RXB is also in the same position. It's just that in the 2 byte one, you don't output the XB. The other important thing to note about RXB here is that this RXB is actually in the same order as the rex prefix as well. So the rex prefix was always 4 followed by something, which was like the bits were WRXB. So these RXB bits are in the same order as the actual rex prefix byte, which means that we can just take the rex prefix byte that we're calculating at the moment and just shift it up by 5, and that will get rid of these things for us and leave us with RXB, which we can then just invert. So if we just invert these and have it shifted up, that will already be in the correct place, in the correct position. And then for the 2 byte case, we can actually just, you know, mask off the X and the B to leave us with just the R bit. Then finally, for a 3 byte VEX, we always start with C4, and for a 2 byte VEX, we always start with C5. Okay, so the way that I will implement these is, well, I guess we'll do some tests first. So let's go to MOVAPS again. So MOVAPS is down here, and the forms here for VMOVAPS are the same as the MOVAPS version, the difference being that there's now this YMM version as well. So for the test for this, we can just copy the MOVAPS tests, but change it to VMOVAPS. So this is one test, and then the other test will just change XMM to YMM. So in this case, we've got extended still, we've got not extended, and we've got memory access for all of those tests. I think that should be okay. That should cover all of the forms that I care about. So let's just regenerate this listing file. This should completely fail. Yeah, mismatch. So encoder test, we'll just take this existing test. This is now going to be op VMOVAPS, that's the only difference here. And then we'll take these and change this. Instead of X word, this will now be Y word. Okay, so now in the forms, we'll basically have the same forms for VMOVAPS, but the difference will be that these can match on X word or Y word. And we'll add a new field to the forms called family, and this will be VEX. I don't know what this is actually called. I call it encoding family. I think maybe the manuals might use a word like group or something like that, but I just call it family. So we'll do type family is bytes, and then we'll do const. So legacy is going to be the default family. Then we'll have VEX, and then we'll have EVEX. So when we match on VMOVAPS, we'll have X word or word. We've got the correct operand encodings with VEC and then VEC mem, or VEC mem and then VEC, and then opcode and map is staying the same as the MOVAPS version. The only difference is the kind of encoding that we're using. So if we just run these tests, oh, I need to add family to the form. So we'll do family is family. Okay, so now what's happening is that I'm still outputting the sort of legacy encoded version. So I've still got like this map byte here, followed by the opcode, followed by the modrm. We actually need to, in this case, C5 is the 2-byte version of the VEX prefix. So C5 is just saying that it's 2 bytes, and then this F8 here is the actual VEX prefix bits that do the work. Then C4 here, because I've got extended registers here that go from 8 to 15, this now requires the 3-byte version so that we can encode those in, for example, there's R, but there's also B needs to be used in this case. And then down here as well, the YMM ones can still use 3-byte because the length is encoded as a single bit in both versions. So again, this is just changing to the 3-byte one because of the extended registers here. So let's just work on this now. If we go to the encoder and go to emit, as we saw from the diagram, everything from the opcode onwards is the same. So this is the opcode onwards, so I don't need to change anything about this. Instead here we can just switch on the form family, and in legacy we can just put all of the stuff that we were doing up until now. And because legacy is the 0 value, it's the default, it means that everything I've done up until now should still work. So we want to take everything to here and put this in legacy, but I actually want to take the VEX prefix stuff out because I can still use that byte in both legacy and VEX encodings. So we'll take the VEX byte stuff out and put it above here still. But we won't output the byte here, we'll just do the simple check for the high byte registers and do the panic here. And then within here, I'll still, before the map, need to do the actual output of the full byte for the legacy encoding. So hopefully this should still work for all of the legacy encoded stuff, which it does. Then I can create a case for the VEX family. So with the VEX family, if we just go to the layout again, so we've got VEX Prefix Layout here. I basically just need to build up these bytes, and so I'll assume that we're going to use the 2-byte VEX and only change it to the 3-byte VEX if it's actually needed. So we can see here that, for example, these are called byte 0, byte 1, and byte 2. So in here, what I'll do is I'll have B0 be equal to VEX 2. This can be a constant, so VEX 2 was C5, was to be a byte equals OXC5. And then the 3-byte VEX was C4, so we'll go C4 with this one. So we'll assume that it's 2, but we'll say, for example, you know, if there's extended stuff used or the map is not the secondary opcode map, then we'll use VEX 3 instead. And so for this, I think what we can do is that RXB can be used in both of these cases. So I'll actually do RXB first. So we'll do RXB first, which is basically just the Rex prefix inverted so that it's 1's complement now, shifted up by, shifted up by 1, 2, 3, 4, 5, 5 bits here. So we'll shift it up by 5. That will cut off the high nibble of the Rex prefix and the W bit of the Rex prefix and leave me with RXB in the inverted state there. So then I can also say that because the Rex prefix is now inverted, I can shift it up by 1 more to cut off the R here and say that if XB is equal to 0, then that means that these are actually being used and I'll need a 3-byte VEX prefix. The other thing I can do is say that if I need a map that is not just the secondary one, then I'll also use the 3-byte. And I'm pretty sure that map here, I've defined it as, it's defined with iota, so I can actually say that if the map is greater than 0f, then we'll do that. So we'll say if RXB shifted up by 1 is equal to 0, then that gives me just the XB, and if that's 0, then it means that it is actually being extended because it's 1's complement or inverted form now. Or if the form map is greater than map 0f, then we'll switch B0 to being B3 instead. Then once we know the size of the prefix, we can basically switch on B0 to say that if it's VEX 2, then we'll do something, and if it's VEX 3, we'll do something else. So we'll sort out the 2-byte VEX prefixes first. So in this case, we basically need the R bit, the VVVV field, the L, and the prefix. So I think I'll add a couple of methods. One will be VVVV, and one will be this PP method. So this one will go on the prefix, and this one will go on the operand. And in the case of VVVV, this is also stored in 1's complement. So it's basically the index register, the register's index inverted, and then shifted up by 1, 2, 3. So it's basically the same as RM. If I go to RM and just copy this, this will be 1, 2, 3, 4, VVVV. We basically just need to take the index, invert it, mask off those low 4 bits, and then shift it up by 3. Oh, sorry, it's basically the same as reg. Sorry, not RM. So that gives us VVVV. Then we need a PP, which can be done as a helper function attached to prefix. So we'll do P prefix. This will be PP, return a byte. So in this case, we'll just do a switch because we know that in the case of that it's prefix 66, then we'll return 1. In the case that it's F3, we'll return 2. And in the case of F2, we'll return 3, and then in the default case where it doesn't have a prefix, we'll return 0. So this basically covers this stuff down here, where 6 is 1, F3 is 2, and then F2 is 3. And these are all encoded in these lower 2 bits anyway, so that we don't need any shifting for these at all. So that gives me a couple of methods that will be useful to use. So we'll go back to VEX2 here. So in the case of VEX2, I'll basically want to create B1. So B1 is going to be, we'll say R is RXB, but we're going to AND with OX80, so that we only get the top bit, the most significant bit. So we're going to put that in, and we'll OR it with the VVVV. So in this case, we'll need some other variable to use as VVVV. Then we'll OR that with a length, which I haven't defined yet, and then we'll do the form prefixes p value. So the length for VEX is always going to be either 128 or 256. So L128, this is basically where L is 0, it says down here. If it's 0, then it's 128. If it's 1, then it's 256. So L is in bit position 2 in both cases, so we can leave it as 0 for 128, and for 256, this would be the value 4. So in this case, it's 0, and 256 is 4. So now all we do is say that L is equal to L128 if width is equal to YWORD, then L is equal to L256. So that gives us B1, and then we can just append, so e.code equals append e.code, B0, B1. Oh, and we need VVVV. So we've got RM and reg being defined up here. I need another operand for the third. So if we need to select a third operand, we need to do that here with the operand encoding. We don't actually have anything that uses VVVV yet, so this will just return the 0 value inverted, which will be 1111, shifted up into the correct position, and we can see here that in the case where it's unused, it must be 1111 anyway, so that's actually correct. So let's just try the tests. Invalid operation. Okay, we've got, I think I need to change these to make sure that they're bytes. Okay, so that seems to have sorted out most of the tests, except for where we need 3 bytes. Yeah, 3 bytes. I think, so we need the 3 bytes VEX prefix, but we're getting the 2-byte one. So let's see, we've got B0 here. Okay, so this is basically just that it's falling into the VEX2 category right now, but I need it to go into the VEX3 one. So this one shifted up. RXB is already the inverted Rex here. I guess what I'll do is just take this, and we'll just do something like 0x88 or something to see that if we're getting it to fall into the correct case. It needs to check. I think the only thing that should be making it fall into the VEX3 case is the fact that they are extended registers being used. So let me just print out this quickly. Maybe what I'll do is I'll just append this in the... Yeah, if I just append this, I can see what it actually is. So we've got RXB. Let's see if it's actually falling into here at all. So it doesn't seem to be going in there at all. Form.map should be fine, so I think it's just this RXB check that's going wrong. So let's just put this on. Maybe what I'll do is say well, let's just do this. So we got in this case is this because, so I've got rex is 4 0 in this case. So in this case where I am shifting up by 5, so that means that I should have RXB here, but then I'm getting 4, so this means that X is being set, which means that this is 0 and this is 0, so that's okay. And then I want to say that I need to check if either of these is 0, basically. So this equals 0 check isn't actually good enough. So maybe what I'll do is, I could just say for now that if I'll just take these checks for now, or just say that rex yeah, maybe for now, just to get this working, I'll just take the is extended checks for RM. So instead of trying to do this bit thing here, we'll just say if RM is extended, or the index is extended, or the map is not 0f. Let's just get rid of this append here. Then we want to do, okay, that's fine now. So this is now falling into VEX 3 because there's an 8 on the beginning. So now I just need to create those 3 byte prefix. So we'll take this stuff here. For the 3 byte one, we can actually just use RXB as is in here. Then we've still got, so then we've got the opcode map selection instead. So in that case, we want to do, so basically got 1, 2, and 3 for the opcode maps. Let's go to the opcode maps here. We've got, this is 1, this is 2, and this is 3. So I should be able to actually output these as is as well. So B1 will be RXB ORed with the bytes of form.map. Then we've got W bits used like rex.w or used for opcode extension. I think for now we'll just say that W is equal to 0. And we'll get to that when we actually need to encode W. So this will be B2. So B2 has W, ORed with VVVV, ORed with L, ORed with the prefix, and then we just output B2 as well. Okay, so that passes all of those tests. So that's basic VEX prefix. The only thing I'm missing here is the W right now. So let's just go back to MOVAPS, and the additional instructions here are all now EVEX. So I'm not going to do all of EVEX right now because there's stuff like these K registers and zeroing masks and stuff. But I will at least do these different sizes without the K masks and zeroing, or the K registers and the zeroing masks. So this will go all the way up to 512. So the same as VEX prefix, there's a layout for these. For the EVEX as well. This again is the same with opcode, modrm, sib, disp, and immediate, but the disp is split into these 2 different ways of encoding, where this disp 8 is like a compressed version of it. So we'll be ignoring this for now. We'll be ignoring K-masks, so we won't be doing anything with AAA. And we'll be ignoring like the upper 16 registers right now. Or maybe, yeah, maybe we'll be ignoring the upper 16 registers right now. And then we'll also be ignoring this zeroing mask and the W bit here as well. Okay, so let's just go to create some tests again. So we've got the EVEX one. So for this, we'll just copy this. I don't know, maybe I won't ignore. Okay, maybe what I'll do is take these ones out. So the problem here is that if we go and look at MOVAPS again, basically if we look at, for example, this first VEX encoding, this is just XMM with another XMM register or memory. If we look at the first EVEX one, this is the same thing. The only difference is that we can use K registers, we can use a zeroing mask, W must be set, and because it's EVEX, it actually allows vector registers 16 to 31. So out of these two, if we have the choice, we should always choose VEX, because this is going to be more compatible with more CPUs, and it's going to be a shorter encoding as well. So the only time we'll need to use EVEX is if we are using one of the features that only EVEX can provide, like higher registers or K masks or K register masks or zeroing masks or something like that. So maybe what for now I will do, just to sort of test the like the selection of this stuff, is that these two will actually select VEX prefixes. Then we'll have these tests down here, which will force a selection of EVEX by using the extended registers from 16 to 31. So for example, if we say 16 and 31 on these, and maybe just like 31 and 16 or something, we'll then just take this test and duplicate it a few times. So this will be YMM, and this one will be ZMM. So this test down here with ZMM will always be EVEX, because VEX can't do 512 bits. But these tests here would normally be VEX. But because they use these extended registers in like the high extended 16 registers, they need to change to saying that VEX is not possible, so therefore we will choose the EVEX encoding for these ones. These ones here are exactly the same as these ones, but they don't have the extended registers that EVEX provides, so these ones stay as selecting a VEX form instead. So this will introduce a bit of a problem in the matching as well. So let's just regenerate the listing. And go to the encoder test. So let's just copy this one. We'll take out this one here. So we're saying this will go from 16 to 31. This one I did as 31. And then this one I did as 16. So we'll have the XWORD version, the YWORD version, and the ZWORD version. Okay, so this should fail. Okay, yep, that all fails. So ZWORD is actually, I would expect this to panic. VMOVAPS. Because this matches on XWORD and YWORD, but this one is using ZWORD. So as you can see here anyway, we'll just carry on with this. So these are all using the EVEX prefix, which always starts with 62. This is the encoding from NASM, but I'm always outputting this 2 bytes or 3 bytes. Here's a 3-byte one, VEX prefix. So this one really should be matching only on ZWORD, so I'm not sure why that one is matching anything at all. Oh, I think it's because, yeah, it's because my matching, if there's at least one thing in there, then that always gets matched. So maybe I should change that at some point, but for now we'll just ignore it. So I basically need a copy of these two, but these ones would have to be EVEX. Other than that, they are exactly the same. And then in this case as well, we could also match on ZWORD. Okay, so now that I've got those forms in, the ZWORD ones are actually matching on that form, so they're not outputting a prefix at all, because I don't have any code for that yet, for all of these Z ones here. But these ones are now incorrectly outputting a VEX prefix when they should be outputting an EVEX prefix. So to test that I'm actually matching the correct form, what I'll do is start by updating the form selection to make sure that VEX prefix, like VEX family forms are rejected if they can't be used, and that should mean that this test output will do the same thing as down here, where it's not outputting any prefix at all for now. So if we go to the encoder and go to the top of emit where the form selection is, what I need to do in here is say in the operands match, I think we'll just change this to, instead of taking in just info, we'll just take in the full operand. And then what we can do is basically just say, this is no longer flags, this is just operand. That means that these op ones here need to do info instead. Then we'll just say, we'll just call this match or something, and we'll say that if it doesn't match, then we'll return false. The default case is to return true, so this should just do the same as it did before. But now we also want to add a helper to, let's say, the operand. So the operand, I think maybe what I'll do is I'll have an extra flag on the operands that say that they require EVEX. So we'll say requires EVEX or something like that. So then that way on these vector operands here, I can just add, to these top 16, these require EVEX. So I can just OR this in here. And then later on when I get to doing stuff like K registers or zeroing masks or something, when that operation is applied to an operand, I can just add that flag so that we can check for it in here. So for example, we'd also say that if the form dot, or if f.family is equal to VEX and op1 dot is requires EVEX or something, maybe we'll just do this in here. So we'll say requires EVEX is equal to this, or op2 or op3 or op4. If any of them require EVEX, then we'll return false. So if we're on a VEX form, but we see that any of the operands require EVEX, then this can't be a match, and so we'll return false. And so now all of the ones that would require EVEX are now skipping over that VEX form and finding the EVEX one instead, and so there's no prefix here because I haven't done any EVEX prefix stuff yet. So let's just go to the encoder and have a look for VEX down here. We basically just need another case in here for EVEX. And we basically just need to fill out the bit layout the same as we did with VEX, but instead for the EVEX layout. So in this case, EVEX always starts with 62, and it's always 3 bytes of prefix information here. So map here is the same. It's 1, 2, or 3, I think, for the different maps. If we just go and have a look, let's see, we've got, yeah, so map IDs are 1, 2, and 3, which are denoted by this. So this is 1, this is 2, this is 3. So this is the same as VEX here. It's just that they've got 2 less bits for it because they didn't need those. Then we've got, you know, RXB are in the same positions as before, but we've got R prime here for extending into the upper 16 for the R extension to go from 16 to 31. We've got VVVV here and then V prime here, and I think X is the one that gets used for the extension of the other field. I can't remember. This one is obviously an extension to R. I think X is the extension for the other one. So yeah, we've got R prime, which is the high 16 for reg. Then we've got X here is the high 16 for RM. And then V prime here is the high 16 for VVVV. But again, VVVV isn't being used in any of the instructions I'm encoding right now. So, you know, that will have to be tested in a different case. Then this L field has been extended as well. If we go and find LL, so let's see, I think LL, is there anywhere that says this? Vector length. So vector length can be used for other things as well, like rounding control. But LL, it doesn't get set to it doesn't get set to 3 for 512 bits, I don't think. It's, oh, here it is. So basically, 0 is 128 bits, which is the same as the VEX prefix. Then 1 is 256. And then this one here is 2 is 512, and then 3 is reserved. So this will give you an undefined opcode exception. So that's just another important thing to note there. Okay, so I guess we'll just start filling these in, basically. So we'll start with, for example, P0 is always going to be a byte of 62. This is always the prefix for EVEX. That's always the first byte. Then we need P1. So P1 is going to be RXB again. And I think RXB is this still stored in, yeah, it's still inverted format. Same goes for R prime, same goes for VVVV, and V prime, and I assume this one, so X doesn't say that it's inverted format, so we'll just have to be careful of that. So P1 is RXB in inverted format, so we'll just take the RXB stuff from here and do this down here. So this is RXB. This one we don't have to choose between just R or RXB, so we can just put the whole thing in. Then we've got R prime. So R prime I'll just call RP, and for now I'll just set this as just being 1, so we'll just have it set. But this is actually bit position 4, so this will actually be 1, 0, so OX10. We'll do R prime into there. Then we've got this fixed 0 here, and there's a fixed 1 down there, so we'll just say P0 fixed maybe. Which I'll just do as, you know, OX00. I don't have to OR this in, but I just want to do it for the sake of completeness. Then we've got the map, which is just going to be form.map, but as bytes, because this is still the same 1, 2, 3 thing. Then we need P, well, that was P, oh, so this is P0. So maybe I won't output this here. We'll just say e.code equals append, e.code. We'll do that. Then we'll do P0, P1, P2. Okay, so this is actually P0. So we'll do P1 here, which has W. So again, I'll just ignore W for now. And W, I don't know if that is inverted or not. Let me just try and find it. So this is 15. I don't know. I think we'll just leave that as 0 for now. Then AAA here. Okay, well, let's just carry on with this this thing. So we've got VVVV. This is still shifted up by 3, so that's the same place. So this is going to be W ORed with VVVV dot VVVV. ORed with V prime. Oh no, V prime is in the next one. This time we've got P1 fixed, which is 0, 1, 2. So this is going to be 4 here. So that gets ORed into there. Then we've got the form prefix. So form.prefix.pp. That's the same because it's still the low 2 bytes. Then we've got Z, which I'm always just going to set to 0 right now because I'm not doing any 0 mask. I don't have any 0 masking flags in the operands right now. So this is for P2. So we've got Z ORed with the length. So this is LL now. So LL we'll say is L. Let's just take these. So we'll do these consts up here. So 128 would be, this one is, they're both 0, so that's still correct. Then with 256, I think this one is set, so this would be 2, 0. Then for 512, I think just this one is set, so this will be 4, 0. And we'll just change this, so this will be start out as 128, and then we'll just do a switch on the width. So in the case that it's Y word, we set LL equal to L256. Otherwise, in the case of Z word, we'll set it to 512. And we'll OR that in. Then we've got B here, which is broadcast or rounding control or suppress all exceptions context. So we'll just leave that as 0 for now. So we'll just put B here. This will be 0. So we'll OR in B. Then we've got V prime. So we'll do VP. Again, V prime, I think this said that it was stored in inverted format. Yeah, inverted format. So I'll just set this as being not set, which will be 1. So that means that this needs to be 0, 8 for this case. And then we've got AAA, which is the index of the K register you want to use, but I'm not doing that right now. So I'll just set that as 0. So after B, we've got V prime. Then we've got AAA, and then we append them all. So let's just see what's broken here. Okay, so it seems like it's mostly actually okay. So if we have a look at this first one here, we've got 16 and 31. So P0, or P0, what we want is 8, 1, but what I'm getting is D1. So let's go back over to here. So basically, if I'm getting D1, that means that this is being set to 1 correctly, which is how it's supposed to be. It wants 8 1, so it wants this. But I am setting 1 1 0 1, I think. So why is that wrong? So X and yeah, it wants 8 and it's getting D. So these top bits are incorrect. So RP is being set. Okay, I think then what I need is like an is. I need like an is extended EVEX or something. Where I basically see if I think I need to check to see if the 5th bit is set. And in this case, it'll also be only if it's VEC, maybe. We'll try this. So we'll do EVEX. What I've got here is RP. So R is always the reg field. So if reg is extended EVEX, then RP equals 0. Okay, so that's brought it a bit closer. So now we're getting C, but we want 8 here. And that's because the other extended EVEX things aren't being done. So X is the one that extends RM. So we've got RXB. This is high 16 register specifier modifier. Let's just say, so V prime is also the same sort of thing. This is basically going to be if VVVV.is extended EVEX, then we would set VP equal to 0. But we're not using VVVV right now. So right now, what happens is that EVEX.x RXB is the next register. So this is still the same as it was before, but it's in the inverted thing. Combine with B and mod RM when SIB or VSIB is absent. So in the case where RM, so if RM is extended EVEX, then we would actually want to set the X in here to be 0. So we would do I think it was this, no, it's and invert equals. In that case, the Rx is 4, so we'd do 4 0, I think, to unset it to say that it's extended. Yeah, so that's it. Okay, so that deals with some basic legacy SSE encodings, basic VEX prefixes with 2 bytes and 3 bytes, and basic EVEX prefixes, although we're missing a bunch of features right now.